Okay, now let's suppose we have r equals cosine theta, and you know from polar coordinates and graphing equations in polar coordinates what that's going to look like, or at least you know how to graph this. We want to describe the region. I was looking for my description here because I didn't remember exactly what it was. And that's not r, that's theta. 0 less than or equal to theta less than or equal to pi over 2. The more I try to make that look like a theta, the more it looks like a blah, but that's theta. Okay, theta from 0 to pi over 2, r equals cosine theta. What does that region look like? Well, we graph r equals cosine theta, starting at theta equals 0, meaning we'll have a point along the x-axis. When theta equals 0, r equals cosine of 0, which is 1. And that gives us this point here. Now, if theta was pi over 4, then r would be square root of 2 over 2, about 0.71. So if we go out to theta equals pi over 4, and actually that angle would be just a little further from the x-axis, but we go out a distance 0.71. Now if this is a distance 1, it's very plausible that this distance here is 0.71. And I'm not going to explain how to do a graph in polar coordinates. You already know how to do that, or should. We've actually had assignments to do that in this course. Okay. And then finally, as theta gets to pi over 2, we get r equals 0 because the cosine of pi over 2 is 0. So as theta sweeps around here, r keeps decreasing and ends up at 0. So this is a picture of our region. Now this little red blob in the middle here is an r delta theta region. Okay, we could draw our delta r, our arc for delta r. Okay, right there would be part of one circle, there would be part of another, so that this is confined within a delta r interval and a delta theta interval. If it has sample point r star theta star, then what's its area? Well, if it's a delta r by delta theta, it's going to then be an r star delta theta by delta r region. Okay, the dimensions of the region will actually be r star delta theta and delta r. So the area of the region will be just as it was here, r star delta theta times, I've written it somewhere. Not sure I ever wrote it down, so let's write it down. I swear it's up here somewhere. Okay, dimensions are r star delta theta by delta r. That's going to be the area of our typical region. And what we're going to end up with, and I did this kind of quickly in class, we were running out of time, and I thought it was a fairly straightforward conclusion. Our integral is going to be described, well, first we describe our region by less than or equal to theta less than or equal to pi over 2, as we say here, and 0 less than or equal to r less than or equal to cosine theta. That's our description of the region. So our integral, and I've written deltas where I should have written d's. Okay, this area expression comes from this, but we're going to the integral, taking the limit as delta r and delta theta approach 0. So we get a dr and a d theta. So here's our integral. Okay, our integral is just of the area. So we're summing up r star delta theta delta r's over this region, taking the limit, and that leads us to the integral, where theta goes from 0 to pi over 2, and r goes from 0 to cosine theta. So for every theta, we have r going from 0 to cosine theta. If theta is 0, we go from here to here. If theta is pi over 4, we go from here to here. If theta is 2 pi over 3, we go from here to here. We get the region. I'm not doing that rigorously, but right now we've done enough things rigorously in xy space that it ought to be clear what we're doing. So we form this integral, and then the integral is easily enough evaluated. Okay, we evaluate first with respect to r. We get r squared over 2. Plug in cosine theta and 0. We're going to end up with cosine squared theta over 2. And take the 1/2 out. We've still got to integrate cosine squared theta. And you do that by one of any number of methods. Okay? So that would be the area of this region right here. Now we go to another example where we have a density function and we want to find the mass within this region. So it's as though we have this flat plate in the xy plane, and the material gets denser as we move away from the origin by a certain rule which is given here, and we want to find the total mass inside of this region. And the way we're going to do that is we're going to ask ourselves, well, what's the mass inside your typical delta r by delta theta region with sample point r star theta star? Once we can answer that, we know what limits to put in the integral because the region is still the same region, and we're going to get an integral that represents that mass. And looking at this, I find that we didn't actually do that. I thought that's what we were doing there. I was working backward across the board. So we will have a video on this one before you see the video for this one. And then I think I will kind of clean this side of the board and do what I just said I was going to do. So next video, this side of the board should be clean, and we should be able to solve the same problem for the same density function, but doing it in polar coordinates.